All right, so our video on 4.7 for some reason didn't translate. So let me work a couple of the problems that were in that video just to show you. And it was all about optimization. And so the first problem looks like this. Suppose we have a rectangular box with an open top, okay, but a square base. So the base is square, the top is open, all right? And we want it to have a volume of 216 cubic inches. But we want to minimize the surface area. In other words, we want to use the least amount of material required to get this particular volume. So the way we're going to do this is we've drawn our picture, we're going to label it. Now it's a square base, so these two dimensions are x and x. And this dimension, let's put it out here, is y. But we don't want more than one variable. We want all x's or all y's. And so this is where we use the little piece of information they give us that the volume they want of this box is 216. So what that means is that the volume of the box is x times y, and we need that to be 216. If that's the case, that tells us that y must be 216 over x squared. And so we're going to use that in place of y. All right, now with all of these problems, with all these optimization problems, after you've drawn the pictures and labeled it, then you read the problem and you say, what is it do you want to maximize or minimize? And so in this case, they say, what is the minimum surface area? So we want the minimum surface area. So that tells us the equation that we need to use. So we need to come up with an equation for the surface area of this box. Well, remember, it has no top. So the surface of the bottom, the area of the bottom, is just x times x, or x squared. The area of each side is, each side is just a rectangle with a base of or of x and a height of 216 over x squared. So that's one side. We have 4 of those sides. So there's the equation for the surface area. So once you have the equation, and now that's what you want to optimize. So that tells you take the derivative, right? Because we optimize always the same way. Let's rewrite this equation as x squared plus what's that going to be? 1064 over x, right? So s prime will be 2x minus 1064 over x squared. And we want to optimize that by finding out when that equals 0. So we set it equals 0. And I'm going to multiply everything by x, or x squared here. Okay, and that gets rid of the fraction and makes it just a little easier to work with. Multiply both sides of the equation by x squared. And so that leaves a 2x cubed minus 1064 equals 0. So I can solve that, right? Move the 1064 over, divide by 2. I end up with x cubed equals 532. And so x, let's move it over here. Let's go over here. So x will be the cube root of 532. So x is about 8.1. So that's what we need. We need our base to be 8.1, right, on a side. And then our the height of this is going to be 216 over 8.1 squared. So it would be, we'll just say y is going to equal about 3.3, just rounding to the nearest decimal, right? And you could real quickly check your work to see that having a box like this gives you the volume that you require. Now, we've rounded off quite a bit, but if I use 8.1 times 8.1 times 3.3, I get 216.513 for the volume. And so I meet the volume requirements, and it turns out that these dimensions of this box will be will have the minimum surface area. And so that is an example of minimizing or optimizing the surface area.